In section 5.4, we're still going to be using a multiplication rule in the long run, but we're going to be dealing with dependent situations. So with dependent situations, we have to first of all talk about the idea of a conditional probability. So a conditional probability, the notation P of F vertical bar E is read the probability of event F given event E. It is the probability that the event F occurs given that event E has occurred. So again, this is going to be important notation, the probability of F given that E has occurred. So the simplest thing is probably to look at an example. Suppose a single card is drawn from a deck of playing cards, a standard deck of playing cards. Find each probability. So if I randomly draw one card out of the deck, what's the probability that card's going to be a king? Well, we've done this problem several times now. That probability is going to be 4 out of 52, or that would be 1/13 if we reduce it. So probability of drawing a king is 1 out of 13. Look at the second question here. We're going to randomly draw one card out of the standard deck of playing cards. We want to know here, what's the probability that it'll be a king given that it's a face card? So if I know it's a face card, right, the question is, what's the probability it's going to be a king? So I'm going to pull back in my deck of cards here. So on the first problem, we have all 52 cards, right? That's our sample space. And 4 of those cards are kings, so it's a 4 out of 52 probability. On the second question, though, we know that it's a face card. So knowing that it's a face card means we're really only looking at these cards here that are face cards. So there are only 12 face cards. Now, of the 12 face cards, 4 of them are kings. So the probability of being a king, given that we have a face card, is 4 out of 12. 4 kings out of 12 face cards. Or that would reduce to a 1/3 probability. So having this given changes the probability. Third question, what's the probability of heart given that it's a face card? Well, the same kind of deal. The probability of heart, well, if I know that it's a face card, I'm only looking at these 12 face cards. And of the 12 face cards, 3 of them are hearts. So the probability is going to be 3 hearts out of 12 face cards. So that would be a 1/4 probability. So again, we call this a conditional probability because we know we have a condition. We know a condition. We know some information about what has occurred. And so that reduces our sample space. I'm going to skip this next piece just for a minute. And I'm going to jump over here to the general multiplication rule first. And then I'm going to come back to this. So keep this handy because I'm coming back to it. The general multiplication rule. The general multiplication rule says that the probability that 2 events E and F both occur is the probability of E and F equals the probability of E times the probability of F given that E has occurred. In words, the probability of E and F is the probability of event E occurring times the probability of event F occurring given the occurrence of event E. So in other words, I'm still going to use the multiplication rule just like I did with the independent events. The difference is that I'm going to have to adjust the second probability assuming that the first event happened. So an example will help make that make a little more sense, I think. Suppose two cards are drawn from a standard deck of cards. What is the probability that both cards will be kings? So I'm drawing two cards. What's the probability that the first card is king and the second card is a king? Now, again, we've already talked about the fact that the first card and the second card are not independent. They are dependent. The probability of the second card being a king is going to depend on the first card, whether or not it's a king. So what this rule is saying is that I'm going to find this by finding the probability that the first card is a king and then I'm going to multiply that by the probability that the second card is a king, given that the first card is a king. So this given or assuming that the first card's a king. Well, the probability that the first card's a king, that's going to be 4 out of 52. The probability that the second card is a king, assuming that the first card's a king, is going to be 3 out of 51, as we've talked about previously already. So again, I'm still just multiplying like we already have done in the previous section, but I have to adjust the second probability, assuming that the first situation occurred. So since I'm assuming the first card was a king, there's only 3 kings left in the deck and there's only 51 cards left in the deck. So now I just need to multiply and see what that is. Well, I'm going to simplify. 4 goes into 52 13 times, so I have 1 over 13. 3 can cancel with 51, leaving 17. So 3 over 51 will reduce to 1 over 17. And if I multiply 1 times 1, that's 1 on top. 13 times 17 is 221. So there is a 1 in 221 probability that both cards will be a king. So what does that really mean? If I repeat my experiment a large number of times, then 1 out of 221 times, I'm going to end up with both kings. Now, just for the heck of it, I'm going to change that to a decimal as well. So that would be 0.0045. So this is approximately 0.0045. So if I were to say, shuffle the deck of cards and draw out 2 cards and look at them, put them back in, shuffle the deck, draw out 2 cards and look at them, put it back in, shuffle the deck, draw out 2 cards and look at them. If I were to do that 10,000 times, then about 45 times out of the 10,000 times, I would get 2 kings. Or if I were to do that 221 times, so I shuffle a deck, draw out 2 cards, see what they are. Shuffle the deck, pull out 2 cards, see what they are. If I did that 221 times, 1 time probably, I would get 2 kings. The other 220 times, I would not get 2 kings. So that's what this probability means. Second question, what's the probability both cards will be hearts? So we're going to look at the probability that the first card is heart. Whoops, I closed that parenthesis. I didn't mean to do that. So what's the probability the first card's a heart and the second card is a heart? Well, that's just like the first problem here. That's going to be the probability that the first card is a heart times the probability that the second card is a heart, given that the first card is a heart, or assuming that the first card's a heart. Well, the probability first card's a heart. If I pull back in my cards here. 13 of the 52 cards are hearts. So that would be a 13 out of 52 probability times the probability the second card is a heart, assuming the first card's a heart. Well, if the first card's a heart, there's only 12 hearts left in the deck, and there's only 51 cards left in the deck. So the probability that the second card's a heart, given that the first card's a heart, would be 12 out of 51. So if I'm going to multiply that, again, I can reduce. 13 goes into 52 4 times, so 1/4 would be that probability. 12 and 51 can both be divided by 3. 12 divided by 3 is 4. 51 divided by 3 is 17. And then the 4s there will cancel. So that's going to be a 1/17 probability. Now 1 divided by 17, that is 0.0588. So again, if I repeat this experiment a large number of times, shuffle a deck, draw out 2 cards. Shuffle a deck, pull out 2 cards. Shuffle a deck, pull out 2 cards. If I did that 10,000 times, about 588 of the times I would get 2 hearts. The rest, I would get something other than 2 hearts. Question C. What is the probability that neither card will be a heart? So now we're looking at the probability that the first card is not a heart and the second card is not a heart. Well, that's going to equal the probability that the first card is not a heart times the probability that the second card is not a heart, given that the first card is not a heart. So what is the probability that the first card's not a heart? Well, we could figure that out a couple of different ways. One, there's 13 hearts, right? So that means there has to be 39 cards that aren't hearts, since there's 52 cards altogether. So add the spades, the clubs, and the diamonds together. There are 39 not hearts. So 39 out of 52 would be the probability that's not a heart, times the probability that the second card's not a heart, assuming that the first card's not a heart. Well, if the first card's not a heart, then there would be 38 cards that aren't hearts left in the deck out of 51 cards left in the deck. So now I can cancel a little bit. Let's see, the 39 and the 52 can reduce to 3/4 because both are divisible by 13. 38 and 51 will not reduce, but I can cancel the 3 with 51. 3 goes into 51 17 times, so that's going to leave 1 up here, 17 down here. And I can't cancel out 4, but I can cancel a 2 out of the 4 and the 38. So 38 divided by 2 will be 19. 4 divided by 2 will be 2. So I'm left with 1 times 19, which is 19, and 2 times 17, which is 34. So the probability would be 19 out of 34, or that would be 0.5588. So if I randomly draw out 2 cards, shuffle the deck, draw out 2 cards, shuffle the deck, draw out 2 cards, if I did that 10,000 times, about 5,588 of those 10,000 times, neither card would be a heart. D, what's the probability the first card will be a heart and the second card will be a diamond? So probability first is heart, and second is diamond. I'm just continuing to do the same thing. So this is going to be the probability that the first card is a heart times the probability that the second card is a diamond, assuming that the first is a heart. Well, the probability that the first card's a heart is 13 out of 52. Now, the probability that the second card's a diamond, assuming that the first card's a heart, is going to be 13 out of 51. It's 13 because if the first card's a heart, there's still 13 diamonds in the deck, but there's only 51 cards left in the deck. Now I can cancel. 13 will cancel with 52, leaving 4. Nothing else is going to cancel. So I'm left with 1 times 13, which is 13, out of 4 times 51, which is 204. And if I take 13 divided by 204, that is 0.0637. E. What's the probability the first card will be a diamond and the second card will be a heart? Do you see the difference between question D and question E? So in D, the question was the first card's a heart and then the second card's a diamond. So there it's heart first, diamond second. Here we're being asked what's the probability the first card will be a diamond and the second card will be a heart. So it's diamond first, heart second, which is a different outcome. So the question is here, what's that probability? So what's the probability the first card is diamond and the second is a heart? Well, that would be the probability that the first card is a diamond times the probability that the second card is a heart, given that the first is a diamond. Well, the probability that the first card's a diamond is going to be 13 out of 52 times the probability the second card will be a heart, given that the first card's a diamond, is 13 out of 51. If the first card's a diamond, then there's still 13 hearts left in the deck, but there's only 51 cards left in the deck. So again, I can cancel, and 1 times 13 is going to be 13. 4 times 51 is going to be 204. So that probability is also 13 out of 204, or 0.0637 if I change it to a decimal. So again, if I repeat the experiment a large number of times, 10,000 times, draw the first card, draw the second card, and put them back, shuffle the deck, do it again, do it again, do it again, do it again. If I did that 10,000 times, about 637 times, the first card would be a heart, the second card would be a diamond. About another 637 times, the first card would be a diamond and the second card would be a heart. So those are the probabilities. They do have the same probability, but they're different outcomes. Now look at question F. Question F's tricky. What is the probability that one card will be a heart and the other card will be a diamond? So probability one card is a heart and the other is a diamond. Now the reason why this is tricky is because this is really an or question in disguise. Okay, it's kind of a combination of ands and ors. So if one card's a heart and the other's a diamond, it's not specifying which is which. So like in question D, the first card was the heart, the second card was the diamond. In question E, the first card was the diamond and the second card was the heart. This question, one heart, one diamond, but it's not really saying which one's first, which one's second. That doesn't matter in this part. It's just a matter of, did you get one of each? So in other words, what could happen here is it could be that we get heart first, diamond second, or we could get diamond first, heart second. Well, that's going to equal the probability of getting the heart first and the diamond second, plus the probability of getting the diamond first and the heart second. I'm going to use the addition rule here, and I can do that and just add these two things together because these two outcomes are disjoint. You can't get a heart first and a diamond second and get a diamond first and a heart second at the same time. You can get one or the other, but you can't get both of these at the same time. Now we figured out what the probability of getting a heart first and the diamond second was. That was right here. That is 13 out of 204. We figured out the probability of getting a diamond first and a heart second. That's also 13 out of 204. So if I add that together, that's going to be 26 out of 204. And that will reduce. 26 and 204 can both be divided by 2. So that would be 13 out of 102. So the probability of getting one heart and one diamond, again, would either be heart first, diamond second, or diamond first, heart second. And that overall probability would be 13 out of 102, which again is just these two probabilities added together. If I do the division, that would be 0.1275, which is essentially just these two things added together. If I just added these two decimals together, I would get 0.1274 instead of 75, and that's because of rounding error. These have been rounded, and that rounding error didn't occur here. Now I want to back up and talk about this conditional probability rule. I think it makes sense to talk about the conditional probability rule after having talked about the general multiplication rule. So if I were to take this right here and solve it for P of F given E. In other words, if I take P of E and F equals P of E times P of F given E, and if I were to divide both sides by P of E, then on the right-hand side, P of E would cancel, and I would be given P of F given E. And on the left-hand side, I would have P of E and F divided by P of E. In other words, this conditional probability, the probability of F given E, is equal to the probability of E and F both occurring divided by the probability of E occurring. And that is what this right here says. If E and F are two events, then the probability of F given E, in other words, that conditional probability, will equal the probability of E and F occurring divided by the probability of E occurring. Now, another way that we could say that, we could use N. N stands for number of. That would be the number of ways that E and F can both occur divided by the number of ways E can occur. And this is kind of how we've been looking at it. We've actually kind of been doing this part on these problems here. The probability of the second card being a king, given the first card was a king, is the number of ways the second card could be a king out of the number of cards left. So we've been figuring that conditional probability this way. So the probability of event F occurring, given the occurrence of event E, is found by dividing the probability of E and F by the probability of E, or by dividing the number of outcomes in E and F by the number of outcomes in E. So take a look at this example. According to the U.S. Census Bureau, 17.9% of U.S. households are in the Northeast. So I'm going to write that down over here. If I randomly select a U.S. household, the probability that that household is in the Northeast is 17.9%, or 0.179. In addition, 5.4% of U.S. households earn $100,000 per year or more and are located in the Northeast. So that second thing that they're telling me is that the probability that a household earns $100,000 or more in a year and is in the Northeast, that is 5.4%. So that probability is 0.054. We want to determine the probability that a randomly selected U.S. household earns more than $100,000 per year, given that the household's located in the Northeast. So we want to find the probability of 100,000 or more, given that the household is in the Northeast. This is what we're being asked to find. So if I know the probability of living in the Northeast is 0.179, if I know the probability of 100,000 plus and in the Northeast is 0.054, can I find the probability of 100,000 plus given that the house is in the Northeast? Well, that is using this idea. The probability of F given E is equal to the probability of E and F divided by the probability of E. So this is my F given E. Now here I kind of wrote this backwards compared to the way this is written, but I wrote it in the order it was stated. Again, this is F given E, so this is E and F, and this is E. Comparing it to here, I mean. So in other words, this probability is just going to be the probability of 100,000 plus and in the Northeast, which is 0.054, divided by the probability of being in the Northeast, which is 0.179. And again, all I'm doing is using this rule, the probability of E and F divided by the probability of E. So if I take 0.054 and divide by 0.179, that is equal to 0.3017 if I round to 4 places. So this is about 0.3017. So again, I'm just finding the probability that both are occurring divided by the probability of being in the Northeast, and that gives me the probability of the 100,000 given that it's in the Northeast.